Math 1143, Section 3.5, Exponential and Logarithmic Equations continued. We're in the process of solving some logarithmic equations. The next one, the logarithm of t minus 8 equals 1.4. So remember, if the base is not indicated, it's understood to be the base 10 logarithm. So we can write the exponential equation equivalent to this and write the argument t minus 8 equals the base number 10 raised to the exponent 1.4. And then we can add 8 to both sides, so we get t equals 10 to the 1.4 plus 8. And 10 to the 1.4, well, we'll just leave it in that form for now. Okay, in the next example, we have log base 7 of x minus 48 equals 2 minus log base 7 of x. So what I would do if I were going to do this one, I would add log base 7 of x to both sides, so we get log base 7 of x minus 48 plus log base 7 of x equals 2. And then, since we're adding two base 7 logarithms, we can write this as a single base 7 logarithm if we multiply the arguments. And we'll multiply x minus 48 times x, which is x to the second minus 48x. And that's equal to 2. Then we'll convert this logarithmic equation into its exponential equation equivalent. So 7, the base number 7 raised to the exponent 2 equals the argument x squared minus 48x. So I'll just write x squared minus 48x equals 7 to the second, which is just 49. And then we have a quadratic equation, so we'll subtract 49 from both sides. X squared minus 48x minus 49 equals 0. And we can solve this one by factoring. Things always work out nicely in this course. So x minus 49 and x plus 1 are the two solutions, or sorry, the two factors. And the two solutions are positive 49 and negative 1. Okay, but in the original equation, negative 1 doesn't work. Negative 1, if you replace x with negative 1, we have a negative in the argument, and that's not permitted. So negative 1 is not a solution. When you replace every x with 49, the arguments are positive. And you can also verify by doing the logarithmic arithmetic that x equals 49 is the solution. Okay, and the next objective, this is objective 3 in section 3.5. Use exponential and logarithmic equations in applications. Okay, so after 10 years, a $2,500 investment is worth $3,729.50. Find the interest rate if interest is compounded annually, then monthly, then continuously. Okay, so we'll write down the function if it's annually. So the amount A of 2,500 times 1 plus r to the t, that's the function. We don't know what r is yet. But we're told that when t is 10, the value of the investment, or the amount in the investment, is $3,729.50. So we're going to replace A with $3,729.50. Set that equal to 2,500 times 1 plus r to the 10. And then we solve for r. So first divide both sides by 2,500. So we'll get 3729.50 divided by 2,500 equals 1 plus r to the 10th. And then we'll just raise both sides to the 1/10th power. So we get 3729.50 divided by 2,500 to the 1/10th. That's equal to 1 plus r. And then we'll subtract 1 from both sides. And we get r is equal to 3729.50 divided by 2,500 to the 1/10th minus 1. And you can convert this to a decimal using a high-powered calculator, and then you'll know what the annual interest rate is. Notice we didn't have to use a logarithm in this one, but we did set up the compound interest formula, which is an exponential function. Okay, in the next part, well, what would we do if the interest was compounded monthly or 12 times a year? Okay, so the function this time would look like a equals 2,500 times the quantity 1 plus r divided by 12 raised to the exponent 12 times t. And then we're told that when t is 10 years, the value of the investment is $3,729.50. So the next part of this is very much like what we did in the previous part. Replace a with 3729.50. Set that equal to 2,500 times 1 plus r over 12 to the 12t. Then divide both sides by 2,500, and we get 3729.50 divided by 2,500. That's equal to 1 plus r over 12 to the... Okay, I made a mistake here. I should have replaced t with 10. So 12 times 10 is 120. And 12 times 10 here is also 120. So the exponent on the binomial is 120 here also. So now we'll just raise both sides to the 1 over 120, and we'll get 3729.50 over 2,500 to the 1 over 120, and that's equal to 1 plus r over 12. Then we'll subtract 1 from both sides, and then afterwards we'll multiply everything on both sides by 12. So I'm going to do both things at once. The last thing we do is multiply by 12, but the step before that, we're subtracting 1 from both sides. So we get 3729.50 over 2,500 to the 1 over 120, and then minus 1. And then we multiply both sides by 12, so r is equal to this value. Okay, finally, if the interest is compounded continuously, then the function for the investment is a equals 2,500 times e to the rt. This looks a lot more compact and easier to work with. So this time I'll remember to replace t with 10 and replace a with $3,729.50. So we get 3729.50 equals 2,500 times e to the 10r. Then divide both sides by 2,500. We get 3729.50 divided by 2,500 equals e to the 10r. Okay, now we can use a logarithm. Now let's just compute the natural log of both sides. So we get the natural log of 3729.50 over 2500 equals the natural log of e to the 10r. But the natural log of e to the 10r is just 10 times r. And then finally, we just divide both sides by 10. And so we'll get the natural log of 3729.50 over 2500. Divide that by 10, and then that's equal to r. Okay, one more problem. Find the doubling time for an investment of $20,000 if the annual interest rate is 9.6% compounded monthly. Okay, so let's write down the function first. So the amount after t years is 20,000 times 1 plus 0.096 divided by 12, because the interest is compounded 12 times a year, and then the exponent is 12t. 0.096 divided by 12, that can be simplified a little bit. So let's, just a minute here. Yeah, this simplifies to 0.008. So let's just write the function a equals 20,000 times 1.008 raised to the 12t. Okay, and we want to find the doubling time. So we want to find how long it takes, how many years t is, for this amount to be twice what we started with. So the way we do that, we'll replace a with 40,000, set it equal to the function 20,000 times 1.008 to the 12t, and then solve this equation for t. And the value t will be the doubling time. So first divide both sides by 20,000. And 40,000 divided by 20,000 is just 2. So we get 2 equals 1.008 to the 12t. T is in the exponent, and we want to solve this equation for t. So now we just use a logarithm. We can use the natural log or the base 10 log. Let's just use the natural log. So then on the left-hand side, the natural log of 2, that's equal to the natural log of 1.008 to the 12t. And then using a property of logarithms, bring the exponent 12t out front, so it's 12t times the natural log of 1.008. And then the last thing we do to solve for t is divide both sides by 12 times the natural log of 1.008. So the natural log of 2 divided by 12 times the natural log of 1.008 is equal to the doubling time. And you can use a high-powered calculator to compute the natural log of 2 divided by 12 times the natural log of 1.008. And that will be a number that you can relate to better than when it's in the exact form involving logarithms. So that concludes the videos for section 3.5 on exponential and logarithmic equations.